Hello everyone, welcome back. This video will focus on the properties of the determinant, and then we will see a relationship between the determinant of the matrix and what that matrix is doing to vectors as a linear transformation. The determinant has a geometric meaning in terms of what a matrix is doing to vectors and to shapes. So to begin with, suppose that we have a matrix A square matrix which has some determinant, and then I go into the matrix A and I swap two of its rows. What effect does swapping rows have on a matrix determinant? The effect of swapping rows is that it changes the determinant to the opposite sign. Let me give you an example of that, for a simple example, just for the sake of time. If I have the matrix 2, 4, 5, 1, and I calculate its determinant, then I would get 2 times 1 minus 5 times 4. So that would be the result, negative 18. Versus if I take the determinant of 5, 1, 2, 4, then I would get 5 times 4 minus 1 times 2, result 18, positive. So swapping two rows in a matrix has the effect of flipping the sign of the determinant. You might be familiar with this property already from your work in Calculus 3 on the cross product. You saw in Calculus 3 that if you cross two vectors together in the order of v first and then w, then that would correspond to a 3 by 3 matrix determinant, which has ijk in the first row, the entries of v in the second row, and the entries of w in the third row. Versus if you take the cross product in the opposite order, that would manifest as swapping these bottom two rows. So swapping w into the second row and swapping v into the third row. And one of the properties that you learn in Calculus 3 is that the cross product, if you reverse the order of the vectors in the cross, you get the opposite result. And so that's consistent with this property that we've named up here. If you swap two rows in a matrix, the result of that determinant is going to be the negative of what it was before. Let's talk about the effect of scaling on a matrix. If I scale a single row of a matrix by the number c, if I scale one single row of a matrix by the number c, then the effect that action has on the determinant is to multiply the determinant by that same value, c. So for example, if I have the matrix 1, 2, minus 1, 1, and I calculate the determinant of that, then I get the result 1 times 1 minus 2 times negative 1. So that would be 1 plus 2, result 3. But if I come in and I scale the first row by a value, for example, if I multiply all the numbers in the first row by a value like 4, then the effect that would have on the determinant is it would become 4 times 1 minus 8 times negative 1. So that would be 4 plus 8, result 12. And so we can see that multiplying that one single row by 4 has had the effect of multiplying the determinant by 4. It's left to you as an exercise in today's problem set, as I recall. What would be the effect on the determinant of scaling the entire matrix by a value, as opposed to just scaling one of the rows? Now suppose that you're dealing with two matrices, matrix A and matrix B. How does the determinant of the product of these two matrices, A times B, compare to the determinants of the two individual matrices, determinant of A and determinant of B? Well, there's a really nice relationship here. Determinant of A times B is equal to the product determinant of A, determinant of B. So the determinant of the products is the same thing as the product of the determinants. That's really nice. Just to demonstrate that and see that in action, let me take a nice simple matrix A being 1, 2, 3, minus 2. And the determinant of the matrix A in this case would be -2 minus 6, result minus 8. Let me take the matrix B to be -1, 4, 1, 2. If I calculate the determinant of this matrix B, then the matrix B would have determinant -2, minus 4. So that would be a value of minus 6. Let's then go ahead and multiply these matrices together and calculate A times B. If I calculate that result using the dot product formula, first row times first column would work out to be -1 plus 2, result +1. First row, second column would be 4 plus 4, result 8. Second row, first column would be -3 minus 2, result -5. And then second row, second column would be 12 minus 4. 12 minus 4, result 8. So now if we calculate the determinant of this product, A times B, it would become 1 times 8 minus -40, and the result being 48 makes sense, 48 being also equal to the product of the determinant of A, -8, and the determinant of B, -6. So that's a little example to demonstrate the validity of this equation here. How does the determinant respond when we take the transpose of a matrix? Let's remember, because this was a long time ago that we talked about transpose, that transpose has the job of taking a matrix and swapping its rows and its columns. So if the matrix A has a row which is equal to 1, 3, a transpose would have a column 1, 3. If the matrix A has a row of 4, 6, a transpose would have a column of 4, 6. So let's think about and let's see how transpose affects the determinant. If we calculate in this example the determinant of the matrix A, it would be in this case 1 times 6 minus 3 times 4, result -6. And if we calculate the determinant of A transpose, which we've written below, this would be 1 times 6 minus 4 times 3, result -6. So in this example, we see an instance of a general property that the determinant of a matrix is actually completely unchanged when you calculate the matrix transpose. So the determinant of A transpose is equal to the determinant of A. Let's practice using some of these properties in a determinant calculation. For example, here, suppose I was given this 3 by 3 matrix and someone asked me, can we calculate the determinant of this matrix, please? Now, from our exercises yesterday, we know that it's really, really valuable when you're calculating determinants to have zeros in your matrix in key positions. In particular, yesterday, we saw that if you have a matrix that has a lot of zeros in the top row, for example, here we had 3 zeros in the top row. In our opening exercise, we had 2 zeros in the top row. Anytime you're calculating determinants, if you have zeros in the top row, that's super lucky because that usually gives you a lot of terms that you can automatically cancel out and you don't have to worry about what is their actual value. So when calculating determinants, we love to see zeros in the top row. Now in this case, we do not have zeros in the top row, unfortunately. But we do have zeros. They are in, right now, the third column. So let me try and do some matrix operations to get these zeros from their current position in the third column to a more useful position in the top row. Call this matrix A for short. The first thing I'm going to do is calculate A transpose. If I take the transpose of a matrix, that's not going to affect the determinant at all, but it is going to turn this column of zeros into a row of zeros. If I calculate the transpose, that'll turn the first row -3, -2, and 1 into the first column. It'll turn the second row 5, 4, 0 into the second column, and it'll turn the third row into the third column, so 6, 1, 0. So by transposing the matrix, I've at least pushed those zeros into a row of the matrix. Now I would love to have the zeros in the top row of the matrix instead of the third row. So I can achieve that by swapping row number 1 and row number 2. And if I swap those two rows, I know that that will have an effect of just applying a minus sign to the determinant. So negative determinant of now, I have those zeros swapped into row number 1. So now that I have written the matrix so that the zeros are in the top row, this makes the determinant a lot easier to calculate, because the only term in this expansion is going to be the first one, the number 1 times the determinant of 4, 1, 5, 6 left behind in this bottom right corner. So that'll be 24 take away 5. So that'll be all in total a determinant of -19. So being able to swap column and row here, being able to swap one row with another, allowed us to manipulate this determinant into one that was much, much easier to calculate. So that's a nice application of those properties to make determinant calculations easier. In the last part of this video, I want to study the properties of the determinant as they are related to geometry. So consider, for example, this matrix M, a diagonal matrix, right? The matrix -5, 0, 0, 4. So we can calculate this matrix's determinant very easily just by multiplying together these values on the diagonal. The determinant of the matrix M here is the value -5 times 4. It is the value -20. So what I would like to explore is, what does this -20 mean? What does it mean that it has a magnitude of 20 units? What does it mean that it's negative? What is that telling you about what the matrix M is doing? So to that end, the first thing that I want to consider is that when this matrix M is acting on vectors in two-dimensional space, you can think about how it acts upon individual vectors, but you can also think about how it acts upon a set of vectors. For example, if I give us a shape here, a set of vectors and a set of points in two-dimensional space, I could ask the question, what does the matrix M do to this entire box? What does the matrix M do to all of the vectors and all of the points inside the box? For example, I could consider the vector v1 that forms the bottom side of this box. Let me call this bottom side of the box the vector v1. So v1 would have the components 2 and 0. If I apply the matrix M to this particular side of the box, let's see where it ends up. M applied to this vector, -5, 0, 0, 4, applied to this vector, gives us a result of -10, 0. So after being manipulated by the matrix M, this vector that points 2 units to the right is now pointing 10 units to the left. You could also do that same action on other vectors in this picture. For example, a vector pointing straight up, forming the left side of the box. That vector, if we call it, for example, v2, would have the entries 0 and then +3 for the y coordinate. And then if we apply the matrix M to that vector, forming the left side of the box, then that will turn this vector 0, 3 into the vector 0, 12. So that's what the matrix does to the vector forming this left side of the box. And then, for example, using linearity, you can figure out what the matrix M is doing to the other points and the other vectors in this box. And if you apply the matrix M to all the points in this box, it turns into this shape right here on the left-hand side. Here is the old box, the original box, here on the right-hand side, and then here on the left-hand side is the new box that has been obtained by applying the matrix M to every point and to every vector in the old box. You can see, for example, that the vector v1 that was originally pointing out here 2 units to the right has now been transformed into this vector pointing out here 10 units to the left. You can see, for example, that this vector v2, originally pointing 3 units straight up, has now been transformed into this vector mv2 that is pointing 12 units straight up. So here on the right is the old box before being transformed by M, and here on the left is the new box after being transformed by M. So notice two things about these boxes. The first thing that I want to notice is that the old box's area, in this case, it's 2 units wide, it's 3 units tall, so the original area was 6. The new box, after it's been transformed by the action of the matrix, the new box's area, it's 10 units wide and 12 units tall. So the new box is 10 times 12. The new box is 120 units. And so the first thing that I would like to notice is that the area of the box has changed. Specifically, the area of the box has been multiplied by a factor of 20. By applying this matrix M to the original box, the area has been multiplied by a factor of 20. Isn't that interesting, given that the determinant of this matrix had a magnitude of 20? The other thing that I would like to notice about the new box as compared to the old box is that it's flipped. The new box is horizontally flipped compared to the original. You can see it in this picture, for example, by looking at what has happened to this horizontal vector v1. v1, which was originally pointing to the right, is now pointing to the left as a result of the action performed by the matrix M. I will ask editor Sam to please replace the box by an actual picture, and then we can compare the original picture to what the picture looks like after being acted upon by the matrix M. Looking at things in terms of an actual picture can also help to reveal that the image has been flipped by the action of M. So isn't it interesting that the box was flipped in the situation where the determinant of our matrix was negative as opposed to positive? So these experiments are supporting two general rules and conclusions about what the determinant of a matrix is telling you. First of all, the magnitude of the determinant, the absolute value of the determinant, tells you how the matrix changes the size of objects. If your determinant, for example, is 5, and you start with an object that has an area of 10, then after applying the matrix to that object, it'll have an area of 50. The meaning of the sign of the determinant tells you whether the matrix acts to flip the object or not. A negative determinant is a sign that the matrix does some kind of flip or reflection as it acts upon the object. So this is the meaning of the magnitude and the sign of a determinant. It tells you how the matrix changes the size of an object in its domain, and it tells you whether the matrix flips or reflects objects in its domain. Now, with that in mind, let's do another example, and let's consider the linear transformation T, whose job is to take vectors in two-dimensional space and project them onto the line y equals x. Let's start by representing this transformation as a matrix. Then let's find the null space of that matrix. And then let's go ahead and find the determinant of that matrix and interpret that determinant geometrically. So as always, when we try to find the transformation, the matrix representing a transformation, the first thing that we do is apply that transformation to the standard basis vectors, because these outputs are going to form the first column of A and the second column of A, respectively. So let's go ahead and project the standard basis vectors onto the line y equals x. And in order to do that, we should try and find a vector that represents that line, a vector that spans that line so that we can project onto that vector. For example, for simplicity's sake, I might just project onto the vector w equals 1, 1. So if I take the first standard basis vector and I project it onto this w that represents this diagonal line, the projection of the first standard basis vector onto w would be found by taking the dot product of that standard basis vector with w, taking the dot product of w with itself, and then using that to scale the vector w. Now, the dot product of E1 with W is going to be the number 1. The dot product of W with itself is going to be the number 2. And if I apply that scalar multiple to W, I get the result 1/2, 1/2. So that would be what happens when this transformation is applied to the first standard basis vector. And so that would form the first column of our matrix A. To find what the transformation is doing to the second standard basis vector, let me go ahead and project E2 onto this vector W. Once again, E2 dotted with W is going to be equal to just the number 1. W dotted with itself is the number 2. So apply that to the W vector, and once again, we get 1/2, 1/2. So using these two results to form the two columns of the matrix A, we find that A is equal to 1/2, 1/2, 1/2, 1/2. Okay, so here is the matrix A that represents this transformation, that represents this action of taking stuff and projecting it onto this line. Now, let's think about what the null space of this matrix would be, or phrased another way, what the kernel of this transformation would be. In this case, there are a couple different ways, again, to answer this question. One way would be to think about this in terms of augmenting the matrix A with 0, the 0 vector, and then row reducing this matrix and interpreting that result. If I row reduce this matrix, this is one is super easy to row reduce by hand because I can just subtract row 1 from row 2. And so I see that this matrix A ends up with only a single pivot column, a pivot column here in the first position. And the second column corresponds to a free variable. I can read this equation as 1/2 x1 plus 1 half x2 equals 0. X2 is free. And solving the first equation, I can say that x1 is equal to minus x2. X2 is just equal to itself. And that means that the null space can be understood as the span of the vector -1, 1. The coefficients on x2 in this equation and in this equation. So the null space of this matrix is one-dimensional. The null space of this matrix definitely has stuff inside of it beyond just the trivial solution. So this is a matrix that is actively destroying or compressing information, which makes perfect sense when we think about what the matrix A is actually doing, right? The matrix A's job is to project everything in two-dimensional space onto this line. So if I start, for example, with a box or with an object in two-dimensional space, and I think about what that matrix will do to that box or to that object, it is going to flatten that entire box and compress it onto this line. And so we lose all the information that is happening perpendicular to the line that we're projecting onto. Everything in this direction is lost. And so we see that affirmed in the null space that we've just calculated. The null space is everything spanned by this vector -1, 1. And the vector -1, 1 points out perpendicular to the line. So it makes sense that everything parallel to -1, 1 is being lost, compressed, and destroyed by this action of projection. So all of those results make sense. So finally, let's find the determinant of this matrix A and interpret the determinant geometrically. My matrix A had entries 1 half, 1 half, 1 half, 1 half. So the determinant would be 1 half times itself minus 1 half times itself. So 1/4 minus 1/4, result 0. So the determinant of our matrix in this case is exactly 0. Once again, let's think about why this makes sense. The determinant tells you how the size of objects changes after the matrix A has done its job. And what we've seen is that if you start with a box in two-dimensional space that has whatever area, area 4, area 10, whatever, when you apply the matrix to that box, it gets squashed and compressed into a line segment. So all the area that we have had has been compressed, and now the result has no area at all. It has 0 area. Because A compresses 2D objects onto a line. A takes objects with non-zero area and makes them have zero area. So a determinant of 0 is a sign that A is doing some compressing. In other words, a determinant that's equal to 0 is a sign that the null space of A is going to have some other stuff in it besides the trivial solution. So this is going to be an important property to keep in mind, particularly as we get into tomorrow's lecture talking about invertible matrices. That concludes today's video. In this video, we talked about the properties of the matrix determinant. We talked about how the matrix determinant is affected by simple matrix operations. We also saw how those properties can be used to help us to calculate the determinant of certain matrices more effectively. We also saw that when you consider what the matrix does, not to a single vector, but to an entire shape or object within its domain, the magnitude of the determinant tells you how the matrix's action will affect that object's size, its area, or its volume. And the sign of the determinant tells you whether the matrix will flip or reflect that object at all.